So Sam Mercier is going to talk to us about cofibrantly generated model categories and the levelwise model structure on spectra.
That's a lot of words. Cool. Yeah, so we're going to start off with a few definitions that we're going to need in order to talk about a important thing for cofibrantly generated models categories, which is a particular criterion that we're going to put on the domains of the sets of generating acyclic cofibrations and cofibrations. So just be prepared for a couple of very boring definitions. So the first definition is of a Kappa filtered ordinal. So given a cardinal Kappa, an ordinal lambda is which is a limit ordinal. So not a successor ordinal or a zero ordinal. Is said to be Kappa filtered if for each S contained in lambda and cardinality of S less than or equal to Kappa, then we have that S is less than or equal to lambda. Oh, sorry, the supremum. So that's a definition. And then we need this definition for this notion of being Kappa small. So we say we have a co-complete category M, Kappa some cardinal again, and a class of maps C contained in M. We say that an object X in M is Kappa small if the morphism, so there's a natural function from the colimit, oh, sorry, for any Kappa filtered ordinal lambda, and diagram F of shape lambda in M, such that F of beta to F of beta plus 1 is in the class C for all beta in lambda. We have that the colimit of, I guess we should probably use alpha here. on the Homs, class of Homs, F of alpha. Okay, so this is one way in which we take a colimit here. And then we get a natural map from this colimit into the colimit on the inside, if that makes sense. And so this is coming from this is coming from so like I guess I should explain what this map is. So if we have, so the upper colimit is the colimit on kind of this sequence. So colimit on x f of alpha Hom x f of alpha plus 1. So we get a co-cone here down to the colimit. Sorry, this is beta in my notes, so I'm maybe making a couple of mistakes. Cool. And then we also get a map from each of these objects to this other colimit. This should be beta. Okay, cool. And this is given by post-composition by the arrows in the co-cone on this colimit here. Does that make sense? And then this is enough to induce a map in between these two objects here. And so, sorry, the condition here is that this is an isomorphism. Is it clear what that map is? And why it's not necessarily always an isomorphism? So this is essentially saying that we can, if we have a map into, this colimit here, we can factor it through one of the I don't know what the word for these objects are, but these intermediary objects that we're using to construct the colimit object.
Could you just go back to the beginning of this definition?
Yes.
So C is a class of maps, I see.
Yeah. And so it can be a proper class. So it doesn't need to be a set. And it will actually be a proper class in our example case when we apply this definition. I promise this is the one dip into this kind of like orders and set theory stuff we're going to do, and then everything else will be straightforward.
I was just wondering about the first definition. Are there any good examples to keep in mind of these filtered Kappa filtered ordinals?
So a good example to think of would probably be the natural numbers in themselves. I think this is kind of what we, I think the I don't know, maybe this is like improper, but most of, maybe I'm supposed to say like aleph null here or something, but that's kind of going to be what most of our examples are going to be. But there's, it's my understanding that we might need to move to a higher ordinal or something at some point, but I'm going to kind of like breeze over those details. If we do. I don't think we do need to for this talk. I think I presented a little bit too complicated of a definition.
And omega filtered is just the usual notion of filtered, right?
Yes, yeah. And so in the usual case, we also call this we call this just small instead of omega small. Yeah.
Oh, I think, wait, sometimes small means kappa small for some kappa, right?
Yeah, and that's how we're going to be using it today. But there's some weird kind of like notion. I can't remember if it's like you can move to a higher ordinal or you can move to a smaller ordinal. But like if it's kappa small for some kappa, you can kind of like interchange your ordinals in some way and play some shenanigans or whatever. Does anyone else remember the details here, or are we comfortable moving on?
Do you want to maybe give us an example of an omega small object in some category?
In a mega small object. Yeah, I have some examples kind of on the next page. But
okay.
Some examples of small objects are like Sn is small relative to the class of cofibrations. And I believe it's in particular omega small. In spaces.
Another good example to keep in mind is an omega small set is a finite set. Also, Jeff asked a question in the chat. He said, what is the advantage to taking lambda to be an arbitrary limit ordinal rather than some regular cardinal?
The advantage is that you can choose any limit ordinal that is like smaller in some sense than kappa. So you find some kappa for which this holds, and then you can choose any kappa filtered ordinal thereafter, and then you get kind of a lambda. It gives you kind of like a space of ordinals to choose from. Is my understanding. Being someone who's like thought about this exactly none recently. So
maybe one other thing that should be said about this is that I think you can also talk about kappa filtered categories. And for some reason here, we only want to think about colimits indexed by ordinals, but there's a more general notion of kappa filtered colimit, which allows more complicated diagrams. And I think those are also worth thinking about.
Okay, I'm gonna move on. Okay. To I think a definition that was presented in the last class, but I missed kind of the latter end of the last class. So where we're going to use kind of this notion. So this definition is of cofibrantly generated model categories. So a model category and is said to be cofibrantly generated if there exists I and j sets of maps such that the class of fibrations, which I think we used F for, is precisely the things that have the rate lifting property with respect to J. The set of cofibrations is things which have the left lifting property with respect to things which have the right lifting property with respect to I. And 3, the domains of maps in I and J are kappa small. For some kappa. relative, sorry, I need to say what relative to what class of map. So relative to I cell and J cell respectively. Okay. Oh, we didn't define I cell and J cell. So I cell and J cell are in particular the closure under transfinite composition. Composition push out. And I think retracts also. So an example is if we, in spaces, pointed spaces, if we take I equal to the inclusion of the n-1 the n-1 sphere into the n disk, and if we take J equal to the inclusion of the n disk into the cylinder on the n disk, and these pluses here mean that we're joining a free base point. Then this will generate the model category structure on spaces. Okay, so a question that you might want to know the answer to is, why is this useful? And so one reason why it's useful is because it gives us a way to describe the cofibrations in such a category. So the cofibrations are in particular retracts of, oh, sorry, this shouldn't include retracts. Retracts of elements of I cell. Sorry, I got confused in my notes. Okay, and then a second reason why we might want to care about this is this gives us a model category in which factorization is functorial. And this is accomplished via a construction called the Boolean construction and an argument called this small objects argument, which we're going to talk about next. So here's a good point to ask questions if anyone has any questions about material presented thus far. Okay, then I'm going to get started on some notation. So given maps I from X to Y and P from X prime to Y prime, let LIP denote the set of all maps G comma H Y to Y prime, where how do we want to do this? Let's do it with a diagram. P and H this diagram commutes. So this is the set of all lifting problems for I and P, is another way to say that, if that's more comfortable to you. Okay, cool. So now what we're going to try to do is we're going to try to construct a functorial factorization for an arbitrary map F in a way where it will have the in a way in which it will be in a member of I cell or J cell, which are so I cell is our cofibrations in particular, and J cell is all members of J cell are, I believe, acyclic cofibrations. This is going to give us our notion of factorization. So let's start talking about the Boolean construction. So we're going to start off with a definition of the first Boolean construction, and then we'll construct it inductively. Okay, so we have this map F from X to Y in our co-complete category M. So M is co-complete. And we want to construct F. We want to construct a factorization of F. So some map I from X to an intermediate object Z, and some map P from Z to an intermediate or to Y or codomain, such that I is a cofibration. And we're assuming we're operating in some cofibrantly generated category. So in particular, that would mean being in I cell, and P is a acyclic fibration. And the other case is kind of the same, except for it's going to be in J cell, and then this P is going to be a fibration. So what are we going to do? We're going to attach a lift for every object that doesn't have a lift in I to X, and then that will give us some object, some intermediate object that is a that will eventually be a cofibration, or that will give us some map that will eventually be a cofibration. So what are we going to do here? We're going to take the sum. So these are in lifting problems between I and F. And we're going to take the coproduct over the domains. And we're going to attach this via the sum over all I and I, sum over J comma H of G. So this is attaching. We're attaching via whatever the kind of the upper part of the lifting problem is, and then over here we're going to take the so these are the coproducts of the I's, and then we're going to this is the obvious codomain. These need to be over here. Okay. Sorry. Okay, and then we're going to take a push out square here. So this is going to give us some object which we're going to call G1 I of F. And then this will be I0. So this is our first attempt at kind of the cofibration we're trying to construct. And this is our first attempt at the intermediary object. And then also by the universal property of the pushout, we have a class of map, or we have a function from this object down to our codomain, which is given by the sum of the lower parts of the lifting problem. So that's the h's. And then we also have a map from x to y here given by f. So this forms a, by the universal property of the pushout, we'll get a map here called P1, which we'll call P1, which is also our first attempt at the acyclic fibration we're trying to make. Okay, so that's the first gluing construction. So next we're going to construct the nth gluing construction via inductive definition. So this is going to be the definition of the n+1 gluing construction. Okay. So we define Gn+1 sub I.
Can I interrupt you for a second? Is there?
Oh yeah, sorry.
Because I think in the original thing you have an F and a G, but now in your diagram you have G comma H. Is that the same G?
So I shouldn't have had a G in my original statement.
Yeah,
there should have only been an F. So these G's and H's are the lifting problems that we're trying to attach cells for, so that we get a cofibration. That's what's going on with kinds of these G's and H's, if that makes sense.
Sorry. I guess my other question was, so far we've only used X to Y, right? We haven't used Y to Z.
No, we're not using Y to Z. So these are our goal, not our not something we're given.
Okay. Yeah. Now I.
So we're trying to construct the Z. Yeah. And our first attempt at it is this G1. No, your question is good. I'm clearly not doing a good job of explaining, but hopefully it makes more sense to everyone now. So we're going to find the n+1 gluing construction, and we're going to find it in terms of this existing one. So the n+1 gluing construction of F is going to be defined to be the first gluing construction on Pn. So with this plus the fact that we have P1 as a base case, gives us a definition of the gluing construction all the way to n. And you'll notice, because this is defined in terms of I, or in terms of G1, we're also going to get an I, I think this should have been I think this should have been P0. Sorry. We're also going to get a, oh, so this should have been, sorry, off by one errors are bounding today. So this should be Pn-1. Okay. I don't know if everyone got all the corrections I made.
It was
so we're defining, oh, it was fine before?
Yeah, you just subtracted 1 from everything.
Well, no, because I want this to be I0.
I
see, okay.
Yeah. So I made a lot of changes. I could have made fewer changes going the other way, but whatever. Okay, cool. And this should be P0 as a base case. I'm trying my best to get the indexes right, but that's never something I'm good at. Okay, cool. So now we're going to define the infinite Boolean construction, which is going to be our intermediary object, that Z that we were looking for. So it's just going to be the colimit or transfinite composition of all these I zeros, or these INs. So we have X going to G1 I of F, and then I1 going to G2 I of F, and then et cetera, et cetera. Okay, and so we're going to get, so it's going to be the colimit of this object. So it's down here. We're going to get a cocone. Colimit of the sequence. We're going to get a cocone like this. And then we're also going to get, okay, and then we also have our Y down here. We also have a cocone to our Y, which is given by this. The first one is F, the next one is P0, the next one is P1, etc. And this is going to give us a, by the universal property of the pushout, P infinity. And this is the cocone or natural transformation between the diagram that we're taking the colimit of and its colimit. That's going to give us our I infinity. So this is our factorization here. So what do I want to say about this? It should be clear from construction that this I infinity is going to be a member of I cell. And the reason is because it's just an iterative pushout of arrows that are members of I themselves. And then finally, a transfinite composition of those pushouts. So that, I just realized no one can see the hand gestures I'm doing on my screen. I'm sorry. So it should be transparent that this is going to be cofibrant. This P infinity, though, it may not be entirely clear that this P infinity is in fact an acyclic fibration if we take, the class I to be I, or fibration if we, go the other way. So that's going to require an argument called small object argument. So this is our first proposition. So the first part is that I infinity is an I cell. And the second part is that P infinity has the rate lifting property with respect to I. So P infinity is in rate lifting property of I. And this is called the small object argument.
So just to be clear, you're doing the case where the domains of the maps in I are omega small, right?
Yes. So I guess another assumption here is, I guess I wrote that assumption like 3 pages ago.
Yeah, I must have just missed it or something.
No, it's not. It's because it wasn't part of the proposition. Assume I is a set of maps with small domains.
With omega small domains, right?
Kappa small for any kappa, I think, is fine.
So I feel like if you want to take a bigger kappa, you're going to have to take a bigger colimit to define your Boolean construction.
Well, if I take a bigger colimit, I could just like append identities on the end or something. I don't know.
No, I mean.
Okay, let's choose omega small.
Like after doing these countably many steps, you may not have a map with the right lifting property with respect to I yet. So you might need to keep attaching more and more cells until until you finally get to something with the like I think to make this art. Well, you can keep going if you want, and we'll see.
Another question is whether there's a kappa for which omega omega is not kappa filtered. I don't know what the answer to that question is, but we can go with omega small, because I think that should be fine. Okay, so omega small domains. Okay, with omega small domains relative to I cell. Yeah, it's like kind of weird. I wrote these notes with like ambient I's and J's, which is probably bad. Okay, cool. Let's prove this. So we talked about A. A follows by construction. And maybe this I infinity should have like some subscript F or B of F or something to indicate that we're considering that F from X to Y in the cocomplete category that we talked about earlier. For B, we're going to have to make a kind of lifting argument. So we're going to consider some lifting problem. Of this form, because we want to show that it has the rate lifting property with respect to everything in I. Because the domain of I is omega small and G infinity I of F, our infinite gluing construction, is the colimit of maps in I cell, there must exist some, sorry, I should probably be writing this down. Because P infinity, wait, what do I want to say? I infinity is in I cell. And the domain of I is omega small with respect to I cell. There has to exist some n in the natural numbers such that G factors through Gn of F. Because this is what it means to be omega small. So let's call, so that means we get a diagram Gn of F, G infinity of F, G prime, which is the factoring through bit. What did we call? We just called it domain of I. Okay, that's a good name. Okay, so that leaves us with this kind of a diagram, such that this commutes, and this is, I don't know, like I infinity sub n or something. I don't know. We can give it some name. And then we get Pn over here, which takes us down to Y. And this attaching map H from the original diagram. or not hashing map, but bottom part of the lifting problem. So now we've re-expressed it in terms of kind of a smaller, an intermediary object that we used in the Boolean construction. But this GN doesn't actually have the maps, the lift for this lifting problem. The successor of GN has the lift, as it were. So we're going to actually have to construct the lift against its successor. So I'm going to do that real quick. Or we have to construct the lift to its successor, and then okay. So now we have Pn plus 1. Okay. So this I here is one of the, if we scroll up all the way back to where we were back here, this I is one of the lifting problems for when we construct, you know, we erase this section here and we put in GN and GN plus 1. It's one of these lifting problems right here. And you know, the G prime is one of these G's up here. So there's actually there's actually there's actually a lift, which is in particular to GN plus 1 I of F, which is given by, if we take iota, which is the inclusion of the codomain of I onto the correct I here, and then the correct lifting problem here, that is going to be, this bottom line is going to be our lift. Does that make sense? So it's going to be how do I say that in words instead of symbols? So this lift right here is going to be, let's give this thing up here a name, eta. And this lift is going to be eta circle iota, where iota is that inclusion of the codomain of I onto the specific copy of the codomain of I that we're attaching, and then eta is the the part of the cocone that goes into the n plus 1 gluing construction. Okay, and that's our lift. And then we get a lift to the actual object that we wanted, which is by post-composing by this I infinity sub n plus 1 or whatever, which is the part of the natural transformation that goes in between Gn plus 1 and the infinite gluing construction. And I think that's it. Okay. Did I burn all of my time? Okay. So then, does anyone have any questions about this argument? Okay. So what we've done so far is we've talked about what it means to be a cofibrantly generated category. We've given a benefit of cofibrantly generated categories, which is that we can use the Boolean construction and the small object argument to construct a functorial factorization method for both types of factorization that we want. A question that we haven't answered so far is, if we choose some I and j, when do we have a, in a co-complete category, when do we have a cofibrantly generated model structure that results from those? And so we're going to state a theorem briefly that tells us when we get that. So consider a co-complete category, sorry, complete and co-complete, so bi-complete, I think is the word that they give that. With sets of maps I, comma j contained in M, such that oh, and a subcategory of maps W contained in M. So these are going to be our weak equivalences. Because we can't determine the weak equivalences just from these sets I and J. This forms a cofibrantly generated model category structure if W has 2 out of 3, which is that if 2 out of 3 morphisms, if we have morphisms like this, if 2 out of 3 of these are weak equivalents, then the third must be. I think they talked about that last time, and is closed under retracts. To the domains of I are small relative to I cell. Omega small. And the domains of J are omega small with respect to J cell. 4 is that J cell is contained within the weak equivalences intersect the left lifting property with respect to the class of maps which have the left lifting property with respect to the class of maps which have the right lifting property with respect to I. So this is just saying that J cell is indeed, the class of maps J cell are indeed acyclic cofibrations. 5 is that the right lifting property of I, so maps which are fibrations with respect to I, are contained within God, relifting property with respect to J. Okay, so things that have the right lifting property with respect to I are contained within the class W intersect the right lifting property of J. So this is saying that they are acyclic fibrations. And 6 is one of 2 conditions. So either this is an equality up here. So these are contained within the right lifting property of I, or the other one is an equality. So the is contained in I. Oh wait. Oh, sorry, I was wrong about that. Or this condition is met. So this is saying that if something is an acyclic cofibration, then it will have the right lifting property with respect to the left lifting property of J. Cool. And I'm going to omit the proof of this. It appears in Barnes's book as theorem 8.6.9. But we're going to use this theorem in order to define and that uses this theorem in order to define and also in order to find and prove the cofibrantly generated model category structure on spectra. And I think we're almost out of time, which is probably bad. I may only have time to define the model category structure and not actually do anything kind of with it. So we've already seen the definition of sequential spectrum, so I'm not going to represent it, but I am going to represent the definition of morphism of a sequential spectrum. So f from x to y, where this is some level-wise map. So it's a collection of fn from xn to yn contained within spaces. Is a morphism of spectra if the following diagram commutes for all n. And this is sigma f. Okay. Does that make sense? Sigma fn. Okay.
So
that
just
makes
to remind
sense.
everyone, this is what I called like a naive morphism of spectra when I first was defining all this. And so kind of the magical thing that we're going to do with the model category stuff is make this into a workable definition that tells us about stable homotopy stuff.
Yeah, hopefully. Okay. So I do want to note that there are, this is a co-complete category and complete category. It's bicomplete. And the way that we construct the limits and colimits is just going to be level-wise. I'll give the colimit structure maps briefly, just to convince you at the very least of that. So the colimit structure maps are going to be, so this is for some functor x from, I don't know, some, I'm just not going to skip over this because the real important thing I want to get to is this adjunction in between spaces and spectra, and I don't know if we'll have time to get through that and the model category structure. So the next thing is, I guess, a remark. So there's an adjunction between, no, we're going to do a definition. Okay, so this is going to be the definition of a shifted suspension spectrum. And this is going to be what's going to construct the adjunction between spaces and spectra, which is going to allow us to give it a model category structure. So this is so given some k in pointed spaces, we can construct a spectrum called FNDK with D in the natural numbers. And this FNDK is going to be defined by, it told me that there were not going to be notifications if I hit do not disturb, and it lied. So it's going to be defined by either the point if n is less than d, or it's going to be the n sphere minus d wedged with k if n is greater than or equal to d. And the structure maps here are going to be the identity on the point in the case that n is less than d minus 1, the inclusion of the point into the zero sphere if n equals d minus 1, and then the structure maps for the sphere spectrum wedged with the identity on k if n is greater than d. Does that make sense? So we're just
do you want
kind
to say
of
smash instead of wedge?
I think I do. The smash product is is the monoidal structure on pointed spaces, right? Okay, cool. Awesome. Sorry, I haven't done math in like over a year almost now. So
It's okay. In LaTeX, it's wedge, which is annoying.
Oh, okay, that's why I'm confused. Okay, cool. So this gives us a way to construct spectra out of spaces. And then we have an adjunction, which is given. So this is one way of taking one direction of the adjunction. This is the left adjoint. And the right adjoint is given by evaluation, the free, as it were, is given by evaluation. It's called ND. And it just takes the D space in the spectrum. And that's the right adjoint, I think, unless I got that mixed up also. And so the last thing I'm going to leave you with is the proposition, which is that we get a cofibrantly generated model category structure. And it has two ways of being defined. So one is that weak equivalences are level-wise weak equivalences. Fibrations are level-wise fibrations. Cofibrations are level-wise cofibrations. In particular, these are going to be Quillen cofibrations, and these are Serre, or these are Serre fibrations, and then these are Serre cofibrations, which I think are, it's called the Quillen model structure though, if I remember correctly or something. So these are also called Q cofibrations in Barnes. And this can be generated cofibrantly by the image under the adjunction of the for all n of the cofibrant generators for pointed spaces. So this is going to be to dn. So this is the image under the functor of the inclusion of the n-1 sphere into the n disk. And then I guess people can probably guess what the so J is, but it's what you would expect. Where n and d are in the natural numbers. Okay, we got there, barely. Okay, I guess I stop now for questions. Thank you,
So
Remy.
it's really that all of these three sets are levelwise?
I think so. But there was, so the next thing that I was going to present was there's kind of an alternative construction of these. There's an alternative criterion you can put on the Q cofibrations, because so if you're levelwise Q cofibration, and then additionally you have the criterion on you that you are indeed a morphism in spectra, you can kind of say a little bit more about kind of what's what you look like, and what you come out with in particular is that there's a I mean, I don't know. There's kind of some additional structure there that I was going to present, but I ran out of time.
So I don't think that it's necessarily true that a map which is a levelwise cofibration is, sorry, a map which has the property that at each level it's a cofibration of spaces is a levelwise cofibration of spectra. I think that the cofibrations, I mean, I think that they're defined by this small object argument, by being I cell for the class I that you wrote down, and that's a stronger condition than being a cofibration for every n.
Oh yeah, that might be true. I'm sorry. Yeah, so you're saying that they are indeed levelwise cofibrations, but being a levelwise cofibration and being a morphism of spectra is not a strong enough condition to be a cofibration in the model category of spectra.
Exactly. Yeah.
Oh, okay. Yeah, I'm sorry. That's probably true. Sorry.
So it generally, like, often you can construct model structures where you can say that the weak equivalences and the fibrations are levelwise or object-wise in some sense, but usually you don't get to say that about all the classes of morphisms.
Yeah. Sorry, I spoke incorrectly. No,
Are there other questions for Sam? Let me stop the recording.